Up till now you have understood the principle behind the design of heat exchanger network. You must have also realized that in some of the cases the design is too complicated and computationally intensive. Thus, to tackle bigger and complicated problems for the design of heat exchanger network, one needs computer software. In this lecture, we will see such a non-commercial software which is called HINT, and we will demonstrate this software, and you can use this software for the design of small heat exchanger networks. Let me explain how to use HINT software. There are many softwares which are available for the design of heat exchanger networks. These softwares can broadly divided into commercial softwares and non-commercial softwares. In the group of commercial softwares, Aspen Energy Analyzer, Super Target, WS Pinch, WS Hen Explorer falls. And in the non-commercial softwares which are available free of cost, the softwares are HINT, developed by Department of Chemical Engineering and Environmental Technology, University of Valladolid, Spain, and the other software is THEN, THEN. In the present lecture, we will learn how to use HINT, as it is a non-commercial software and available free of cost. This software can be downloaded from the website given in the screen. There is some material which has been published in Education for Chemical Engineers by Angel Martin and Fidel A. Mato, can be used by the students to learn more about HINT. The software is easy to download and install in a computer. Now, we see after installing in a computer, you get an icon like this. This is a HINT icon, and when we double click, the HINT software runs. The GUI of the HINT software can be divided into three parts. The bottom part or the bottom section, this is the bottom section, is a table that can be used to introduce the thermal properties of the streams and can be called as stream table, where stream, its definition, type, heat type, T1 and T2, which are initial and target temperatures, the H enthalpy and MCP data are available. The central section, this is the central section, is used to display different diagrams such as composite curves, grid diagram and the Venn diagram. The left portion, which is this, displays auxiliary diagrams on a smaller scale as well as a property sheet of the selected element of the grid diagram. All this we will explain by using a small problem. This is the area where delta T minimum, which is a crucial parameter in the design of HENS, can be changed. Now, let us take a small problem and demonstrate it. So, to start with, we go to the streams and then we go to the add. Now, it opens up a window to enter the stream data. The stream data can be of two types. One is non-linear type, another is linear type. This is a linear stream data where MCP is constant, and this shows a non-linear stream data where MCP changes with temperature. Now, we start with the non-linear stream data, which is seldomly used in demonstration purposes, but we start with this. So, we click the radio button of non-linear stream data, and then we go to the enthalpy. It opens up a table like this, and in this table we can fill a non-linear stream data which comprises of temperature and enthalpy. Now, we take a small problem for filling the non-linear stream data. Here you see the temperature and enthalpy, 180 the enthalpy is 0, 160 enthalpy is minus 800, and so on so forth, and in the last temperature is 70 where enthalpy is minus 2400. This is a data for a hot stream where the temperature is changing from a higher temperature to a lower temperature, and this stream is giving heat to the system, and that is why the enthalpies are negative. So, we again come to this table to fill this data. So, I will fill then I press add. This temperature is 140, the enthalpy is minus 1200, then again I press data. This temperature is 120 and this enthalpy is minus 1600. Then again I press data. This enthalpy is 100, this temperature is 100 and the enthalpy is minus 2000. Again I press data. This temperature is 80, enthalpy is minus 2200. The last temperature is 70 and the enthalpy is minus 2400. So, once I fill this data, this is the enthalpy temperature diagram which is visible here, and this can be used in the computation of N. So, we cancel this and now we go for linear stream data. So, I again open the stream data table and let us take a small problem where there are 2 hot streams and 2 cold streams. This is shown in table 1, 4 stream problem for load integration and utility predictions. This is the table where there are 2 hot streams and 2 cold streams. The supply temperature of the first hot stream is from 180 to 75. Its Cp, which is basically MCP, is 30. The second hot stream's moves from 240 to 60, the Cp is 40. The first cold stream C1 is 40 to 230 degree, the Cp is 35. The second cold stream is 120 to 300, the Cp is 20. So, we are going to feed this data and see how the program deals with it. Now, this is stream number 1, the description is H H1. Now, the supply temperature is 180 and the target temperature is 75. I want to introduce the MCP data, so I click this radio button and enter the MCP data as 30 given in the problem. While inserting data, it can be inserted in two mode, MCP mode and delta H mode. So, if I try to introduce delta H, I can on this radio button and introduce my delta H, which is 3150 in this case. But however, we will for this problem we will introduce the MCP data and not delta H data, which is 30. Then I go to the next stream, I press the add button, this number changes to 2 and the second stream is H2. The supply temperature is 240, the target temperature is 60 and the MCP value is 40. So, I go to the next stream now, I put add, this is C1, the first cold stream, its supply temperature is 40 and its target temperature is 230 and the MCP value is 35. I again press add, this goes to the fourth stream, the stream number is C2, its supply temperature is 120 and its target temperature is 300. Now, I have completed my problem and I can press OK. Now, whatever data I have fed, it has come to here, all the stream data. You can match, this is H1 100, this is a hot stream, the heat type is sensible and the supply temperature is 180 and the target temperature is 75, heat exchange is 3150 kilowatt and the MCP value is 30. So, the complete stream table has come to this. Now, this shows the grid diagram and here we see the composite curve, a small composite curve, and this shows about the streams. So, this shows the first stream H1 and the supply temperature 180, target temperature 75. I can press this. So, if I want to see the data of stream 2, I can press this stream 2. If I want to see the data of stream 3, I can press this stream 3, it comes to the cold one. If I want stream 4, I can press this. So, in short, we can also see the complete data from here also, or we can also see from here. Now, after we have fed the data, then we can, these menus are available for further processing. I can see different diagrams by pressing the diagram menu. If I want to see a composite curve, I can press this, I get the composite curve. It is in a small it is a big composite curve. I can reformat it for going to the format statement. I can change this width and height, say suppose I make it 20, I make it 20. I can change the fonts of the axis scale, legend, axis titles, etc. I can write down the x axis title, y axis title, and other things can be changed from here. So, when I press OK, this enlarges. This enlarges the composite curve. Now, I take a second problem of data feeding, and that is given here. The second problem, it is a 4-stream problem where there are 2 hot streams and 2 cold streams. H1 changes from 140 degree centigrade to 50 degree centigrade, Cp is 2 and delta H is minus 80. So, let us feed this and see what happens. So, I go here, it shows me the last problem. So, I have to press here new and then I press stream and add. So, in this case H1 and the supply temperature is 140, the target temperature is 50 and the value of MCP is 2, then I add, it changes to 2. So, the second stream is H2, the supply temperature is 90, this target temperature is 40 and the value of MCP is 6. A third stream is C1, cold one, and the supply temperature is 30, target temperature is 150 and the value of MCP is 2. We go to the fourth stream, this is C2, the supply temperature is 70 and the target temperature is 125 and the MCP value is 3. Once all data related to the stream table has been entered, we can press OK. So, the stream table appears here and the grid diagram appears here. In the grid diagram, you see that this line corresponds to pinch line. The hot pinch is 90 degree, the cold pinch is 80 degree. The first stream moves from 140 to 50 and the enthalpy exchange is minus 180. The minus sign shows that it is a hot stream. The MCP value is 2, shown here. The second stream starts from the pinch itself, it is a hot stream, moves from 90 degree to 40 degree centigrade. It exchanges a enthalpy minus 300 and its value is 6. The first cold stream, it is C1, which the stream number is 3, moves from 30 degree to 150 degree. It exchanges 240 units of heat. That means it requires 240 units of heat to be heated from 30 to 150. Its MCP value is 2. This is the fourth stream, which is second cold stream, starts from 70 degree, goes to 125 degree, exchanges 165 units of heat and its MCP value is 3. Now, this shows how to feed the data using this computer, using this computer program, which is hint. Now, we will go for a small problem and we will show you how to do energy targets and unit target calculations using this hint. Now, for this we take up this problem. This is table 2 problem. Here also there are 2 hot streams and 2 cold streams, and using this we will show you the energy target and unit target calculations using hint. Now, we start with a new problem here. So, we go to the stream, go to this add. Now, here you will see that in this problem the delta T minimum is 10 and here this delta T minimum is 10. So, we do not have to change it, and if we will have a different value we can change the delta T minimum from here. Now, we enter the data. This is H1 140 and this is 50, MCP value is 2, add second stream H2, supply temperature is 90, target temperature is 40, MCP value is 6, add this is third stream, this is C1 30, supply temperature, target temperature is 150 and MCP is 2, and fourth stream this is C2, supply temperature is 70 and target temperature is 125 and MCP value is 3. So, we press here OK, the stream table appears here. We can check this appears to be OK. Now, this is our hot composite curve and this is our cold composite curve. So, if I see the composite curves, this is my hot composite curve and this is my cold composite curve. Now, I revert back to my grid diagram here. Now, you see if I press this, then this stream in this composite curve starts from here to here, it becomes green. So, this is available from here to here, and if I press this, it is available from here to here. Now, if I press this, it appears into the cold composite curves. This goes from here to here, and the second one, this is from here to here, and some part from here to here. So, what I mean that when you press a stream, its contribution in the cold as well as hot composite curves is visible in this small diagram. So, this again we go to the composite curve. If I want to enlarge it a little, so I can go here, I can add this to say 20 and to this make this 20 make OK, it enlarges. So, this is my hot composite curve and this is my cold composite curve. The relative position of these two curves depends upon this delta T minimum, and delta T minimum is the distance from here to here, the vertical distance, where the two curves are closest to each other. Now, from this the hot stream can give heat to this cold stream, but from here onwards there is no stream available to give heat to this cold stream. So, this has to be given by a utility, and here also if I draw a vertical line from here to here, the hot stream from here to here are able to give heat to the cold stream. From here onwards there is no cold stream which will take heat from this hot stream, and hence this has to be taken by a cold utility. Now, if I go for energy target, I can praise this. It gives me a cascade diagram which is called PTA. I get the PTA here. It shows minimum temperature difference 10, heat duty is 175, that is QH minimum is 175 kilowatt, and cooling duties which is QC minimum is 250 kilowatt, and the pinch temperature is 85. So, to get hot pinch temperature I have to add to this delta T minimum by 2, and to get the cold pinch temperature I have to deduct from this data, that is 85 cold temperature delta T minimum divided by 2, which is available in the stream diagram. Now, this energy target which is shown here is dependent on this minimum temperature difference. So, if I change minimum temperature difference here, say make it 20 and press OK, then what I find that this value changes. Now, this is 225 and 300. I can change it further to 30 degrees centigrades. This again changes 245 to 320. Again I can change it to 40 degrees centigrade. Again this changes. I can make it to 50 degrees centigrade, it further changes. So, what we observe that if we change delta T minimum, the energy target changes. Now, this shows the minimum number of heat exchangers. This is unit target. Now, if I change delta T minimum, this unit targets also changes. If I make it 10, then I find that my units target is 7. So, from this table I can find out the energy target as well as units target. Now, if I want to get a complete picture of this, then I can go to a different menu. This is streams, this is cascade, diagram. Just a minute. So, I can go to the delta T minimum analysis. I can go to the here. So, I can fix up this minimum temperature difference as 10 to 50 and number of points 50, and I say OK. It shows how the hot utility and the cold utility are changing when delta T minimum is. I can go to this further. I can ask that how the pinch temperature is changing. This pinch temperature is changing like this when the delta T minimum is changing from say 1 degree centigrade to 50 degree centigrade. I can also see that how my minimum number of heat exchangers are changing when the delta T minimum is changing from 1 to 50. So, this is how. So, we see around 20 degree value of delta T minimum, there is a sudden change. Below this the number of units required is 7, and after this the number of units required is 6, that is minimum number of units required for the heat exchanger. So, we see the effects here. Now, if I want to change the, we again go to the stream grid diagram. If I want to change the MCP of a certain stream, it also affects the grid diagram. Let us see it. Let me change it to 10, and then I say OK. It does not change. Now, it has changed. Now, you see that once this changed to 10 in place of 2, the whole grid diagram changes. The value of the pinch, which was earlier 1980, changes. The placement of streams also changes. So, I go back to 2 and you observe the change. Now, you see this has completely changed. So, we conclude that the MCP value of the stream affects the grid diagram and also the composite curves. The delta T minimum value affects the utilities, that is QH minimum and QC minimum values and units target. So, by these examples, now we are able to understand how the energy targets and unit targets are computed and what are the different parameters which affect the energy and unit target. We will take the same problem, that is table number 2, to demonstrate other features of this software hint. Now, if you go to the diagram menu, then you have different diagrams are available: composite curves with utilities, grand composite curve, available temperature difference, grid diagram, exergy composite curves, exergy grand composite curves, available exergy, etc. So, we are not going to use this exergy composite curve and exergy grand composite curve and available exergy, but we will use all the above diagram, that is composite curves with utilities, grand composite curves, available temperature difference, grid diagram, delta T minimum analysis I have already shown you, and loops and paths. So, the next diagram is our Grand composite curve. So, if I press Grand composite curve, I see a Grand composite curve here. So, you can directly draw your Grand composite curve using this software, and you can take a printout from here using the print menu. Now, if I go to this second, that is available temperature difference, it shows me the available temperature difference. It is drawn between a T cold and T hot. We will discuss a lot about this when we will go for the remaining problem analysis and driving force plot. In the Grand composite curve, from here to here it shows the hot utility requirement, and from here to here it shows the cold utility requirement. You all know about the Grand composite curves. So, if you want to draw, you can use this software. Then if you go to this streams, you can add stream using stream command, you can delete a stream, you can split a stream, you can find out the cascade, this is the cascade, and then you can use the feasibility. This feasibility menu is used for the design of heat exchangers. It has got two parts, above pinch and below pinch, and above pinch and below pinch rules can be used to design a heat exchanger network. This gives you the area target and this gives you the cost target. Now, in the heat exchanger menus, you can add a heat exchanger, you can delete a heat exchanger, you can go for the area and cost calculations, and it shows the results in which it gives you the details of all the heat exchangers available in the heat exchanger network, and this can be used for remaining problem analysis, which gives correct direction to a heat exchanger design. When we are using our own utilities, that means user defined utilities. Now, if you see this hint program uses the utility in two ways. If you do not give cold and hot utilities, the hint program itself assumes cold and hot utility depending upon the stream data. It also gives you a facility to define your hot and cold utilities, and with this add menu you can add a cold and hot utility. The delete menu deletes cold and hot utility. Combine menu, it combines the hot utility and the cold utility with the stream data. So, this is the stream data, and when you use this combine, it combines the hot utility and cold utility. You must have seen that for area targeting, we can combine the hot and cold utility with the stream data, and we can go for the area targeting. It also gives you the cost data. In the loops and paths are used for identification of loops and heat transfer paths in a heat exchanger network. When we go for the design of a heat exchanger network, the first design is a MER design, maximum energy recovery design, and then maximum energy recovery design is further modified to get a low cost heat exchanger design by avoiding, or by, you can say, the pinch is violated in that, to save the number of units. When we will talk about the design, we will see that the MER design can be modified or improved upon by breaking the loops. So, here in the loops and paths drop down menu, you get all those facilities which are used to break the loops and to detect the temperature pass or enthalpy pass through which the heat can be transferred from hot utility to the cold utility. This gives you the diagrams, this gives you the tools, different tools. So, in a nutshell, we have seen that what this program can do, and these are the small icons through which this is icon where through which I can go to the composite curve. This is icon where I can go to the Gantt composite curve. This is icon where I can go for the delta T minimization. For that I have to give the cost data, that is why it is prompting me to give cost data. This gives you the grid diagram. So, these icons are basically used when we do not want to use these drop down menus. Now, we take a problem, new problem, which will show us the area target. We know that there are different targeting schemes in which energy target is a, then units target and then area target. So, we will now take a problem and demonstrate the area target. So, this is the problem which is given in table 3, a 5 stream problem for cost targeting and area targeting. Basically, for the cost target, we will have some more data which are required in the area target. You will see in this table that for area targeting, we need the stream data plus the heat transfer coefficient data for all the streams. Here we can add the utilities. Here there are two utilities, one is steam and the other is cooling water. Steam is transferring heat through latent heat and cooling water is transferring heat through sensible heat. The supply temperature here is 300 and 299, and for cooling water it is 20 supply temperature and target temperature is 60. Here we will see that the temperature is taken for the steam is 300 to 99. We know that the steam heating is a constant temperature heating, it should be taken 300 and 300, 300 instead of 300 and 299 it should take 300. But if I take 300, then my computation of Cp will be infinite. Further, if you see a practical problem, when a cold stream is heated by steam, there is a pressure drop from the location where steam is injected to a location where is steam drawn out. So, due to this pressure drop, the temperature drop will also occur, and if I am taking this temperature to be 300 and 299, I am not committing any mistake, because this is in heat balance and in the computations no error will be introduced. Now, let us start the area targeting using this table 3 data. So, we start introducing the data. So, this is stream data, add, this is H1 159 59, 77, the value of MCP is 22.85, the second is H2, the supply temperature is 267 and target temperature is 80, and this is 2.04. The third is H3, there are 3 hot streams, supply temperature is 343 and target temperature is 90 and MCP value is 5.38. The fourth is C1, the supply temperature is 26, the target temperature is 127, MCP value is 9.33. The last one is fifth stream, which is a cold stream, it is called C2. Supply temperature is 118 and target temperature is 265 and target temperature is 265 here and MCP values is 19.61. Now we have fed our stream data, but we have not fed the frame heat transfer coefficient. Now this can be handled in a two way. In the first case, we will not feed our cold and hot utilities as given in the table, stream table. So we have already fed the stream data, we say OK. Now we have gone to the stream data and area target. Now in this, using this tabular format, we will feed the heat transfer coefficient of different streams. If I see this, it has been written stream 1 and heat transfer coefficient is 2 kilowatt per meter square Kelvin. So default data of heat transfer in hint is 2 kilowatt per meter square and Kelvin. So we here see stream number 1 2 kilowatt. If I change this stream to 2, still it is 2 kilowatt, to 3 2 kilowatt, to 4 2 kilowatt, to 5 2 kilowatt, to 6 2 kilowatt for 5, because we have 5 streams. Now utility, we see the utility number 1, which is heating, hot utility. Its heat transfer coefficient has also been taken 2 and the temperature has been taken 348. If I go to the cold stream, again the heat transfer coefficient is 2 and the temperature of the cold stream is 1. So these are the default values of heat transfer coefficient in the hint. But we can change this, like in our problem the heat transfer coefficient of stream 1 is 0.1. So I write is 1. So that is a problem in this software. You have to keep this decimal value intact. If you delete this, there is a problem in entering. So 0.1. So, and then I go to 2, then I delete this 2, but I keep the decimal value, and then I put it here 0, 4. Then I go to the stream number 3, and the heat transfer value is 0.5. Stream number 4, the heat transfer value is 0.01, and for the 5th stream this is 0.5. I am not entering the heat transfer values of the utilities here. The steam is 0.05 and the cooling water is 0.2. I am not entering these values, and do not consider these values, the heat transfer coefficient values are very accurate, because in the problem we have taken some representative values for showing you the calculation. Now, if I do this, it clearly shows that my area target is 3523.29 meter square. The number of minimum heat exchange, that is unit target, is 8. So, directly I get a value here. Now, what I can do, so if I go again, go to the area target, I see the value is 3643.33. The earlier value was wrong because it has not executed. Now, it has executed completely this software, and hence the area target, when I am not feeding the hot and cold utilities and computer is taking default values of hot and cold utilities, the area target appears to be 3643.33 meter square. Now, let us try to give the values of the heat transfer coefficient of utilities. So, my first utility is heating. So, here the coefficient is say 0.5, and the second utility, this coefficient is 0.2. So, this is 0.2. Okay. So, if I say OK, so it changes, the value of area target changes. Now, you must be wondering that how to feed the temperature levels of the cold and hot utilities. So, let us see how to do it. Now, you see here the minimum temperature difference is 10. If I make it 20, my area target will also change. You see, this has changed. So, by changing the temperatures, you can also see that the area target changes. Now, if you go to the here, that is a utility. Now, I can do it press, this is cooling utility. Say I am passing on the latent heat, the supply temperature is 300 in our case, and target temperature is 299. So, I say OK, this. So, it exchanges a heat of -1295, and it makes it sensible because here the temperature is changing to 300 to 299. Basically, I have approximated the latent heat transfer to a sensible heat transfer. Then say I say plus, it is a cooling, it is not a latent heat. So, I have to make it sensible, and then this temperature is 20 and this temperature is 60. So, I say OK, this adds, say that this adds. Now, I can go to the combine to add these two utilities. So, if I draw this, when it goes here, the value is added up, heating values, and the cooling by 300 degree, 300. Let me check. Oh, there is a stream which is 343. So, we have to increase the temperature of the hot utility, then only it will appear. So, let us change. So, I make it 400 degree, say 360 will also do, 360 and this 359. So, my this line shows my hot utilities, which is above the highest temperature of the Grant composite curve. The cold utility, the lowest temperature is my 26. So, cold utility 22 60 may work. So, this shows you the cold utility line, and this shows you the hot utility line. So, I can combine them . There is some. So, I can go to the area target again, and I see the area target now changed. So, this result which I get is when I am utilizing user defined hot utility and cold utilities. So, I get a area target, which is this. Now, I can also see that how the area target changes with delta T minimum. So, if I do this, I get a curve like this. So, when delta T minimum is increasing, the value of the area target, that means area which is required for the total heat exchanger, is declining. And this shows that when delta T minimum increases, the fixed cost of the heat exchanger network decreases. Thank you.